Okay, greetings one and all, and welcome to this math lesson. In this lesson, we will be considering the topic number theory. Number theory. Let's begin. Okay, let's consider this question. It says, from the set of numbers, we have negative square root of 3, 3 and 1 over 7, 0, 10 over 3, and 5.7. And this bar on top of the 7 indicates that the 7 continues on and on and on forever. So those are the numbers that are inside of this set. It says write down an integer. So we have to look at these numbers. We have 1, 2, 3, 4, 5 of them. And from the set, they want us to identify an integer. Okay, first of all, what is an integer, right? Integers, by definition, include all whole numbers and negative numbers without fractions and decimals. So when you're looking at integers, you cannot include fractions. So 2 over 4, 1 over 4, 1 over 5, all of those things, they are fractions and you cannot include them. Neither decimals, so decimals do not count as integers. So 1.5, 2.3, 7.8, they are not integers. But what are integers then? Examples of integers include -3, -2, -1, 0, 1, 2, 3, and so on. So these are going to be your whole numbers. So you're looking at positive whole numbers, you're looking at negative whole numbers, and you're looking at 0. That's what we mean by our integers. And so if we look at it, we have negative square root of 3. That's going to be a decimal. We have 3 and 1 over 7. That's a mixed fraction. That don't count. We have 0. 0 is a whole number, so that's definitely an integer. 10 over 3, that's a fraction, and that reduces to a decimal. And 5.77 continuing on, well, definitely that is a decimal, so it's not an integer, so the answer is only 0. Only 0 is an integer from the set. Now, from the set of numbers, we're going to write down an irrational number. What do we mean by irrational number? Irrational numbers are real numbers that cannot be expressed as a simple fraction or ratio of two integers, and their decimal representations are non-terminating and non-repeating. What does that mean? Well, when you say a decimal representation is non-terminating, that means it does not end, which means it continues on and on and on. When you say it's non-repeating, you mean that it doesn't have a consistent repeating pattern. All right. So like 0.33333, that's recurring, that's repeating, it has a consistent pattern, or 5959. So, or like 7.59595959. That's repeating, continuing and continuing. But for irrational numbers, it continues on forever and it doesn't have a consistent repeating pattern with it. So what number is what number out of the set is an irrational number? Well, it can't be 5.7 because that continues on and on and on. And plus, yeah, that it can't be 5.77. It can't be 5.7 because it continues on and it has a pattern. That's the problem right there. If it just continued on and on, that wouldn't be no problem, but it has a pattern, and the pattern is 777. So it cannot be an irrational number, so it's definitely not that. 10 over 3, you cannot write an irrational number as a fraction, so definitely not that. 0 whole numbers, integers, are not irrational, they are rational. All right, because you could write 0 as 0 over 1, and that could be written as a fraction. Okay. And then 3 and 1 over 7, we could change that into improper fraction, and we could express it as a fraction. So that doesn't work. This is a mixed fraction. So the only thing I'd be left with is negative square root of 3. A negative square root of 3 is an irrational number because if you express that as a decimal, its decimal representation is going to be negative 1.732050808 and continuing on. So this is definitely an irrational number, the only irrational number of the set. Let's move on to the next question. It says, from the set of numbers, we have 22 over 7, 3.14, and pi. Write down an irrational number. Well, what is an irrational number? These are numbers that cannot be expressed as a simple fraction. So that means 22 over 7 immediately is not an irrational number because it's a fraction, all right? And 3.14 is definitely not an irrational number because it's a terminating decimal. It stops. It has an end, right? It only has a finite number of numbers at the end. So it ends. It has a stop, right? But irrational numbers, if you have them in its decimal form, they do not stop. They do not stop. They continue on, and they don't have a consistent repeating pattern, right? And so the only thing that we're left with is just pi, and pi is definitely an irrational number because if you look at it, we have 3.141592654. It's like, notice that it continues on, so that means it's non-terminating, and it doesn't have a consistent pattern. It's like, it's not like 14141414. It isn't like 151515. It isn't like 77777. It doesn't even have a pattern. And so definitely pi is an irrational number. Okay, let's look at this one. This one says from the set of numbers, we have the square root of 25, we have 17, we have 121, and we have the square root of 32. They say write down a perfect square. What is a perfect square? By definition, a perfect square is a number that can be expressed as a product of an integer multiplied by itself. For example, 121 is a perfect square because 11 squared equals to 11 times 11, which is going to be equal to 121. There are numerous perfect squares. So you look at stuff like 4. 4 is a perfect square because 2 times 2 is 4. Okay, 9 is a perfect square because 3 times 3 is 9. All right, and then you have 16 is a perfect square because 4 times 4 is 16. And then 25 is a perfect square because 5 times 5 is 25. And then 36 is a perfect square because 6 times 6 is 36. And then 49 is a perfect square because 7 times 7 is 49. All of those are perfect squares. And so definitely 121 is a perfect square because 11 times 11 is 121. Back to irrational number, we know that irrational numbers are real numbers that cannot be expressed as a simple fraction. So they cannot be expressed as a simple fraction of two integers. And that's very important. They cannot be expressed as a simple fraction of two integers, and their decimal representations are non-terminating and non-repeating. So if we look at these, remember I said that whole numbers are rational. They are not irrational. So 17 and 121, not, they immediately don't count because they are rational numbers. They are not irrational numbers. So 17, because if we look at 17, we can write 17 as what? 17 can be written as what? 17 over 1. And that's a fraction, okay? And it's a fraction of two integers, all right? And so definitely it's not an irrational number. Same thing with 121. And no whole number, for that matter, is a rational number. Because if you look at 121, 121 can be written as a fraction of two integers, 121 over 1. So because every whole number can be written as a fraction, so irrational numbers, whole numbers are not irrational numbers. They are rational numbers. Now, how about the square root of 25? That's interesting. But the square root of 25 is definitely 5. Okay, so the square root of 25 is 5, and 5 is a whole number. And so whole numbers are not irrational numbers. And so definitely square root of 25 don't count, right? So the only thing that we're left with is the square root of 32. And the square root of 32, if we put it in the calculator, it's going to be 5.656854249 and continuing. It satisfies all the criteria because it's non-terminating, which means it doesn't end, and it's non-repeating, which means that there's no consistent pattern. If you look at, there's no consistent pattern at the end when it comes to its the the numbers at the end. So you look at 656. It's not like it's saying 656, 656, 656, 656. It's 656, 854, 249. It's like it's all over the place. It's not, there's no consistent pattern. And it continues on forever and ever. So it's definitely an irrational number. Hopefully this video, you found it helpful. Thank you for watching, and I'll see you in the next video.